Yeah, so thank you so much for the opportunity to speak here. So I'm going to tell you a geometric story about Schubert polynomials and how you can realize some of their new combinatorics through a geometric setup. So this is joint work with Zach Hamaker and Oliver Pechenik. Okay, so we're going to start just by reviewing Schubert polynomials. I'm going to give a combinatorial definition or two, but if you saw Carola Mazaris's lovely talk, you got a nice overview of a lot of their combinatorics. So Schubert polynomials, they arose from the study of the complete flag variety. And so the complete flag variety, you can think of it as a quotient of the general linear group by the spiral of upper triangular matrices. And inside of the complete flag variety, there's this special family of subvarieties called Schubert varieties. And each Schubert variety defines a class in the cohomology ring of the complete flag variety. And the Schubert classes, they're particularly nice because they're a linear basis for this ring. And so often what we do is we try to multiply two of these Schubert classes and express them in this basis and understand the coefficients. And so we know for geometric reasons that these are non-negative integer coefficients, but kind of explicit combinatorial understanding of these coefficients is a bit elusive, except in special cases. So if you would rather not think about Schubert classes, which are sort of geometric objects, thanks to Borel, there is a presentation of the cohomology ring as a quotient of a polynomial ring. And Lascaux and Schutzenberger, they defined Schubert polynomials to be a choice of coset representatives for the images of the Schubert classes under Borel's isomorphism. So the initial definition was recursive, so you start with some top Schubert polynomial, and you apply these things called divided difference operators to get the rest. There's also double Schubert polynomials, which are just richer versions of the single Schubert polynomials. So instead of just having x variables, there's also x and y variables. And to get from these double Schubert polynomials back to single Schuberts, you just set all the y's equal to 0. So the moral of the story is if you can say something about double Schubert polynomials, you might as well, because it encapsulates everything that's going on with single Schuberts. And these double Schubert polynomials, they tell you about torus equivariant cohomology of the complete flag variety. Okay, so let's get kind of a combinatorial definition for Schubert polynomials. So we're going to do this by way of these objects called pipe dreams. And the way I like to think about pipe dreams is it's a certain tiling of the n by n grid. So on the main anti-diagonal, you always just have to have these upward elbows. And everywhere below, you have these kind of blank tiles. But then the interesting stuff is happening above this anti-diagonal, where you can place either these bumping tiles or these crossing tiles. And you want to fill the grid with n pipes, and you want them to start at the top and they'll end at the left. This is kind of forced by these conditions. And the interesting bit is pairwise, you want pipes to cross at most one time. So this gives you something called a reduced pipe dream. But if you saw Carola's talk, she also talked about these non-reduced ones where you just allow more crossings. So the way we start to get polynomials out of these combinatorial objects is each pipe dream gets an associated product of binomials. So what the binomials are tracking is the rows and columns that the crossings appear in. So for instance, I have this crossing in row 1 and column 2. And so I'm going to associate to that crossing the binomial x1 minus y2. So again, they're just tracking rows and columns where the crossings appear. And pipe dreams happen to be uniquely determined by where these crossings happen. Okay. So the theorem I'm writing Fomin Kirillov, who did this double version, but also Bergeron and Billy, who wrote pipe dreams first in this sort of grid configuration. But the double Schubert polynomial is a sum over pipe dreams that trace out your permutation W. And so here, for instance, in the case of 2, 1, 4, 3, there's 3 different pipe dreams that trace out that permutation. And we get 3 different products of binomials, and we just add them all up together. So again, if you care about single Schuberts, you just set all the y's equal to 0, and you get a perfectly lovely formula for single Schubert polynomials. Okay, but newer to the scene are these bumpless pipe dreams introduced by Lamley-Shimizuno. So they look on the surface very similar to pipe dreams in that they're a bunch of squiggles in a grid, but now we have 6 different tiles that we're allowed to use. And they're called bumpless because this bumping tile from the pipe dream is no longer allowed, so no bumps allowed. But we fill the grid with a bunch of pipes. This time they're starting along the bottom, ending along the right, and we still maintain that pairwise they cross at most one time. So we can look at how these things trace out a permutation, and we can associate to them a weight, which is again a product of a bunch of binomials. But this time, the binomials are not tracking the positions of the crossings, but rather they're tracking the positions of the blank tiles. So for bumpless pipe dreams, the blank tiles are the important part. So for instance, here we happen to have a blank tile in row 1 and column 2, and that gets associated this binomial x1 minus y2. And so we have these combinatorial objects, and the theorem of Lamley-Shimizuno is that you can express the double Schubert polynomial as a weighted sum over bumpless pipe dreams that trace out your permutation. So again, we have another expression for our double Schubert polynomial as sums of products of binomials. And if you put them side by side, if you just care about the single version where you set all the y's equal to 0, there's a way of lining up pipe dreams and bumpless pipe dreams. And Gao Huang, they gave a nice bijection, a very explicit procedure to translate between these two perspectives. But if you also want to carry the y variables along for the ride, you run into problems because you can see already in this small example, there's no way to match up a pipe dream and a bumpless pipe dream in a way that preserves the weight polynomial. But if you expand these out and compare them, you'll see that indeed they are the same polynomials, just 2 different expressions for them. The title has ice in it, so I feel compelled to say a brief word on ice. You can think about the 6 vertex model, which is kind of a 2-dimensional idealized version of how water molecules freeze to become ice. And the 6 vertex model, if you kind of ignore the arrows that are pointing up and pointing right in these configurations, you see these things that look like bumpless pipe dreams popping out. And so indeed, like for each orientation of these interior vertices, they're corresponding to one of the types of tiles that was a building block for our bumpless pipe dreams. Here, I've drawn one that happens to have pipes crossing more than once, but if you just call this thing a non-reduced bumpless pipe dream and you allow yourself a larger set of objects, these pipe dreams are in bijection with configurations of the 6 vertex model. And actually what this observation gives you is Lascaux, in this unpublished preprint from 2002, he explained how to write down Grothendieck polynomials, these k-theoretic analogs of Schubert polynomials, in terms of configurations of the 6 vertex model. And so using this translation, you can extract the formula of Lamley-Shimizuno for double Schubert polynomials from Lascaux's work. You just have to kind of flip things around and check that this bumpless pipe dream combinatorics is compatible with what he was doing with the 6 vertex model. This is where the through ice comes into the story. Oh, sorry, there's something in the chat. Oh, just Starry likes the blue because blue for water and ice. Yeah, that was a conscious choice. Okay, so now we're going to move to a geometric perspective from which we will hopefully extract some of this combinatorics of Schubert polynomials. So we need to start by getting some sort of understanding of these things called matrix Schubert varieties. So let's start with Schubert determinantal ideals. I'm not going to give a proper definition because I just don't really have time, but there's some sort of generalization of determinantal ideals. And so they're generated by a bunch of minors of a generic matrix of different sizes that are prescribed by the permutation. And so here, this kind of rough cartoon that I've drawn, we have what's called the Rotha bumpless pipe dream for a permutation. It has no upward elbows floating around. And you can kind of look at all the different blank tiles that you see, and you can count how many pipes appear north of these tiles. So here, these ones have nothing above them. This has one pipe above it, and this has two pipes above it. And what this is going to do for us is it prescribes rank conditions on certain submatrices. So we want to take, for instance, this one is telling us that this submatrix that I'm highlighting in blue has rank at most 1. And to make it have rank at most 1, we're going to carve out 2 by 2 minors. And so this generating set that I've written down is Fulton's special generating set for these matrix Schubert varieties. So yeah, for these Schubert determinantal ideals. So then these are connected to matrix Schubert varieties, which bring us back to Schubert varieties in the flag variety. So what a matrix Schubert variety is we take this Schubert variety that's living down in the flag variety, and we pull it back along this natural projection from the general linear group down to the flag variety. And so when we pull back the Schubert variety, we can also then include it into matrix space, because every invertible matrix is just a matrix, and take its closure. And when we do this, we get some affine algebraic variety. And this is what Fulton called a matrix Schubert variety. And so the theorem of Fulton is that these Schubert determinantal ideals carve out the matrix Schubert varieties, and they're exactly the right conditions. You have this as a prime ideal. So yeah, we can study, in other words, the Schubert variety using something that we know about the matrix Schubert variety up here. So I'll make that statement more precise in just a bit. So the way we associate a polynomial to a matrix Schubert variety is every matrix Schubert variety defines a class in the torus equivariant cohomology of the space of n by n matrices. And without really telling you what torus equivariant cohomology is, there's a way that you can compute them axiomatically. So these classes, they're preserved under nice degenerations, like taking Grosvenor degenerations. If you have nice enough unions of things, you can just add their classes. And this normalization axiom says if you have a coordinate subspace, the class is very easy. In this setting, it's going to amount to a product of binomials given by the variables that you're zeroing out to get your coordinate subspace. So the theorem of Freire-Riemanni and Knudsen-Miller is that the torus equivariant class of the matrix Schubert variety is the double Schubert polynomial. And then as a consequence of this, using these kind of natural maps that are arising from studying various flavors of cohomology for various spaces, you get that the single Schubert polynomial represents the Schubert class in the Borel presentation of the cohomology ring of the complete flag variety. So there were potentially lots of different choices you could make for coset representative, but this singles out the Schubert polynomial as a geometrically natural choice of representative. So kind of if you want to take this axiomatic approach to understanding this torus equivariant class, there's a recipe that you can do. So you fix whatever your favorite term order is. Knudsen and Miller, they happened to like anti-diagonal term orders. So you fix a term order, you compute the initial ideal with respect to that term order, and then take a primary decomposition. And this gets you to a situation where it becomes relatively easy to compute these torus equivariant classes. So in this case, if we have a permutation 2, 1, 4, 3, it's generated by these two different minors. What anti-diagonal term order means is the lead term of a minor is just the product of the variables on the anti-diagonal. And so here, the lead terms, they have no common variables. This is a Grosvenor basis. We can take lead terms to generate the initial ideal and take, in this case, a prime decomposition. And we can use this prime decomposition to get an expression for the double Schubert polynomial as a sum of products of binomials. And if you've been paying very close attention, this particular sum of products of binomials might look familiar because it's the same one that we got from pipe dreams. So the primes that are showing up are in bijection with pipe dreams for our permutation. And so this is giving not only an explanation for the torus equivariant class, but the combinatorics, this pre-existing combinatorics of pipe dreams is now taking on a geometric meaning. So indeed, this always happens. So Knudsen and Miller, they showed that Fulton's generators are Grosvenor under any anti-diagonal term order. That in turn means that the initial ideal is radical. You can take a prime decomposition, and when you do that, you see pipe dreams are indexing the primes, or in other words, the coordinate subspaces. So this gave geometric naturality not only to Schubert polynomials, but also to their combinatorics in terms of pipe dreams. But if you're like me, an anti-diagonal term order is not the most natural term order. So you might wonder, well, what happens if I take, for instance, like reading order, just a diagonal term order? So these diagonal degenerations, they were studied in a special case for vexillary permutations by Knudsen, Miller, and Yang. And so there's a very lovely analogous story in this setting. First of all, they showed that Fulton's generators are only Grosvenor if you have a vexillary permutation. So outside of this, there weren't candidates for diagonal Grosvenor bases. And then in this case, primes are indexed by combinatorial objects called flagged tableau associated to the vexillary permutations. So something I showed is that vexillary bumpless pipe dreams are in bijection with flagged tableau in a very natural sort of way. Here I'm just flashing a picture because I don't really have time to go into the bijection. But an upshot of this means that diagonal degenerations of vexillary permutations are governed by bumpless pipe dreams. And so you could, of course, wonder, well, how generally does this hold? So what you do is you look at your first non-vexillary permutation, 2143. Here, Fulton's generators aren't Grosvenor, so you have to fix it somehow. And here what happens to work is if you just zero out Z11 in this matrix, then you get things where the lead terms are different. You have a ready-made Grosvenor basis. And so we take lead terms, we take prime decomposition, and lo and behold, we see pipe dreams for 2143, or sorry, bumpless pipe dreams for 2143. And so in this example, we're seeing a geometric explanation for pipe dreams. And so you might just rush out and say, yay, prime decomposition is given by bumpless pipe dreams. But that doesn't happen in general because there's this pathology that diagonal degenerations can fail to be radical. There can be some scheme theoretic weirdness floating around, and then you have to be a bit more careful. You have to look at multiplicities of coordinate subspaces. But bumpless pipe dreams have kind of the same pathology built in to compensate for this, in that you can have two different bumpless pipe dreams for the same permutation, which have the same set of blank tiles. So this sort of example and some computer code led us to conjecture that bumpless pipe dreams label set theoretic components of diagonal degenerations with multiplicity. So the multiplicity of a coordinate subspace is just counting bumpless pipe dreams for your permutation with the correct set of blank tiles to specify that coordinate subspace. So in trying to solve this conjecture, we thought about, well, how can we get a Grosvenor basis? And so one of the cheapest tricks that you can try is just to zero out these single variables in the larger minors that you're taking. And so you can ask, well, when are these things that we called CDG generators Grosvenor bases for diagonal term orders? So with Zach and Oliver, we were able to show that if you have a specific class of permutations, I'm not going to tell you what this class is, but we called it Banner. The CDG generators are a diagonal Grosvenor basis, and then the Knudsen-Miller style result holds. These coordinate subspaces are being indexed by bumpless pipe dreams. And we also conjectured a pattern condition, a pattern avoidance condition for when we expected CDG generators to be Grosvenor. And so this pattern condition was proved by Patricia Klein, and she used liaison theory. And so in more recent work with Klein, we were able to show that you can find a diagonal term order so that the irreducible components in the limit are labeled with multiplicity by bumpless pipe dreams. So in particular, the existence of these diagonal term orders give a geometric naturality to bumpless pipe dreams for your permutation. And with that, I'm a bit over time. So thank you so much for your attention.
Thank you, Anna. Thanks a lot. Any questions for Anna? Okay, so you're hoping to show that bumpless pipe dreams can have the same role as pipe dreams for Knudsen and Miller that they used.
Yes.
So right, and that's certainly true for Vexillary, and then you hope to extend beyond that, right?
Yeah, and so we're able to show that there exists, like for every permutation, there exists a diagonal term order so that the Knudsen-Miller style result holds. And then the tricky part is we expect it to hold for all diagonal term orders, but for instance, things get complicated even for a Lex term order. So there's still definitely more to understand here. Yeah. But there exist situations in which bumpless pipe dreams are as geometrically natural as pipe dreams.
Mm-hmm. And the conjecture is that you could possibly make this work in general, right?
Yeah, yeah. So for any diagonal term order.
And when you showed the Fulton generators, you showed bumpless pipe dreams there on that slide, but Fulton generators were defined independently, right?
Yeah, what I'm doing is this is really just the Roth diagram of a permutation. If you take the bendy corners and make them like hard corners, that's how people normally draw Roth diagrams.
That was the Roth diagram.
Yeah, okay. I just, for time, kind of shoved that by the wayside. But really, there's always a special bumpless pipe dream, which is just the Roth diagram of your permutation. And you can get the rest by iterating these sort of droop moves of Lamley-Shimizono.
Okay. Okay, thank you. Other questions?
Yes, I have a question.
Yeah.
Yes, Martin.
Look at, for the usual pipe dreams, you can, an alternative description is just keep the dots or the filled the elbows, just keep the elbows. Mm-hmm. And as you showed, this does not work for bumper pipe dreams if you just keep the empty boxes.
Yeah.
If you keep the empty boxes and something else, do you get uniqueness?
Oh, there's all sorts of different pairs you can take. So I think like knowing empty boxes and crossings is enough. Knowing, for instance, upward elbows and downward elbows is enough. So horizontal and vertical edges, there's different pairs definitely that you can take. Yeah. Yeah.
And is there something which occurs to you most natural?
Oh, yeah, I don't, well, so if you take like, for instance, downward elbows and upward elbows, then you see that these are actually alternating sign matrices secretly. So that's often how I like to think about these. And this is, again, just popping out of the 6 vertex model sort of connection. In the literature in studying the 6 vertex model, bumpless pipe dreams, they show up as osculating lattice paths if you draw them the right way. So So these objects have been well studied, but just never as Schubert calculus, except for this work of Lascaux and then later Lamellais-Maisonneuve.
Thank you very much.